Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. And the title of this lecture is Qualitative and Numerical Approaches Done Light. You may be interested, this is the final content contribution on which you will be assessed this summer. Next week, the lectures will be enrichment lectures, and you can learn without worrying about being assessed. I do want you to get your money's worth, however. I've talked previously about there were three fundamental kind of approaches. You could approach things analytically, and that's what we did most of the time in this course. That's most of your notes look like this, I think. And that's going to be the character of the proctored final that happens. And the proctored final, and also the enrichment efforts actually. And so the proctored final will be 10 problems and is being proctored on 7/21. And so it will fall into this category, and I will say more about that later, very soon, but later. We also have a qualitative thing, which we're talking about tonight, and a numerical thing, which we're talking about in this suite of lectures as well. And there will be not only these 10 problems, but there will be 4 take-home problems. And the 4 take-home problems are not proctored, but they're to be submitted by 9 p.m. on 7/23, our last day this term, to Blackboard. One of them will be using a calculator in an engineering kind of problem over here, analytical. One of them will be qualitative, and 2 of them will be numerical. Again, more about these very soon. But now let's begin with the lecture. So qualitative approaches, and this is subtitled Solution Curves Without a Solution. So let us imagine for a moment that we have in front of us a first order differential equation that looks like dy dx equal f of xy, and let's further imagine that we can neither find nor invent a method for solving it analytically. Such things really do exist. Now this is not as bad a predicament as one might think, since differential equation itself can sometimes tell us specifics about how its solutions behave. So we will begin talking about analyzing these things qualitatively. And one of the ways that we'll do this is by sketching what is called a direction field or a slope field. Now, sketching a direction field by hand is straightforward but time-consuming. It is probably one of those tasks about which an argument can be made for doing it once or twice in a lifetime. I'm going to assume you've done it once or twice in your lives, and so what we're going to do is be much more efficient, and we're going to be doing this stuff using some computer software. But computer software has to be programmed, so there is that trade-off. So in contrast to what we've done before, technology will be manifest in this material. In this lecture, I use some general purpose available software called Windplot, and it's freeware, and this guy was a champion of it. He will be missed, and it actually does a lot of really cool things. And many of the things that I will be showing you tonight I did in Windplot. Here is a link for some more sophisticated software, and this is written in Java and maybe interfaces with MATLAB. Okay, so let's move on then. So in this portion, we'll see that qualitative questions about the properties of solutions can be addressed. For example, how does a solution behave near a certain point? We're going to talk about attractors, repellers, and semi-stable situations. How does a solution behave as x goes to infinity? And this can often be answered when the function f depends solely, that was dy dx equals f of xy, so this is f of xy depends only on y. And we're going to begin, though, by talking about these direction fields. And let's begin by reminding ourselves that a derivative dy dx of a differentiable function is the slope of the tangent line at points on its graph. So what we're going to do is we're going to consider dy dx equal f of xy, and we're going to systematically evaluate f over a rectangular grid and draw lines that are in the slope. And the collection of these line elements is called the direction field or slope field of that differential equation. Now visually, the direction field suggests the appearance or shape of the family of solutions, and so it may be able to see at a glance how it behaves. So here is the first example that I did. I did this in Windplot, and I have just dy dx equal 0.2 xy, and you see immediately it plotted all these slope fields for me. And then what I did is I just went around and clicked various places, and it solved initial value problems, and it drew curves that went through the points that I clicked on. So this is the family of curves that we would have, and there are many more elements, but I have it representative of what happens there. I know how this behaves when the absolute value of x gets large, and I actually know quite a bit about the solution just from looking at that, the shape, and in fact, more or less, the graph of the solution. Here, I was doing something different. I was supposed to be solving an initial value problem where dy dx equals sine of y. Again, notice that this depends only on y, and I was supposed to solve this for y at 0 equal 1.5. Now, I was lazy and did not type that in. I just went over and clicked, and I guessed, and I didn't guess perfectly, but you see it graphed what happens, and I see much about the behavior of the function. Notice that what is happening is, as x gets large, what happens is this gets closer and closer to, and you might guess, oh, that number is pi, because that's the 0 of sine of y. We're going to pick this up in